Implicit differentiation is how you deal with equations that have x's and y's mixed up in them. You still want to be able to find dy dx, even though it's not a function. So, for example, let's say I have xy squared plus x squared y squared equals x cubed minus 7, something like that. And I have to find dy dx. Because we're taking the derivative with respect to x, and what that means is we treat x as the variable. Y is, we don't know what y is, so we don't know what dy dx is, so we need to use a chain rule and kind of give ourselves a placeholder when we take the derivative of y with respect to x. Okay, so what do I mean by this? So I have x times y squared. I need to take the derivative. This is a product. Using the product rule, I have the first times the derivative of y squared is 2 times y, and the chain rule says I need to take the derivative of the inside and pull it out. The derivative of y is, well, I don't know. That's why I say dy dx. Plus the second, y squared, times the derivative of the first, which is just 1. So all this came from that first expression. Okay, so now I've got an x squared, y squared. Again, I've got the product rule. So I want the first, x squared. The derivative of the second is 2y dy dx, plus the second times the derivative of the first, 2x. And that equals 3x squared. So let's write this a little bit nicer, gather like terms and that sort of thing. So this first expression, I tend to like to write my numbers in the front. And dy dx. Y squared times 1 is just y squared. Here I have 2yx squared, or 2x squared y, times dy dx, plus 2xy squared. And that equals 3x squared. So now we want to solve for dy dx. So we look for the expressions that have dy dx, which is this one and this one. These guys stay. Anything without a dy dx goes to the other side. So on the left, I have 2xy dy dx plus 2x squared y dy dx. On the other side, I have 3x squared minus y squared minus 2xy squared. So now we've got our dy dx's on the left, our non-dy dx's on the right. So to solve, I need to suck out the dy dx, or factor out the dy dx. And I have dy dx times 2xy plus 2x squared y equals, and copy all that over again. Now, just like when you have 2x equals 4, you divide by the 2, I've got the thing I'm solving for times something gross. I'm just going to divide both sides by this gross thing. So I'll have dy dx is equal to 3x squared minus y squared minus 2xy squared divided by 2xy plus 2x squared y. And that's what dy dx is. If I wanted to find the slope at a particular point, then I would plug my x coordinate, my y coordinate in here to figure out what the derivative is at that point. Another type that you'll run across is when the x's and y's are inside of another function. So what I mean by this, here it was nice. All my dy dx's stayed on the outside. And I not inside of a parentheses. But I could have something like tan of xy is equal to 7y, let's say. To find dy dx, I've got the derivative of tan of something. Well, that gives me secant squared of that thing. But then I need to multiply by the derivative of the inside. And the derivative of xy is, well, I've got the first times the derivative of the second, dy dx, plus the second times the derivative of the first, and the derivative of x is 1. So now my dy dx is locked inside of parentheses. So I'm going to have to bail it out in a minute. Over here I have 7 times dy dx. So to get the dy dx out, I have to distribute this thing on the outside, the secant squared of xy. So I will have, make sure I push this up far enough. Secant squared of xy times, I'm going to stick that x in front so it doesn't get sucked into the secant, times dy dx, plus y times secant squared xy. And then just copy this over. Now all my dy dx's are free and out and about, so I'm going to make sure all my dy dx terms are on the left and everything else is on the right. So here I have x secant squared of xy times dy dx plus y secant squared of xy. Oop, forgot what I was doing. That's going to go the other side. Bring the 7 over. And then the secant's coming over minus negative y secant squared of xy. Now at this point I have to factor out a dy dx and then divide by what I get. And I'm running out of space, so I'm actually going to, I'm not going to do that. So factor out the dy dx, I'm left with x secant squared of xy minus 7. And on the other side I have negative y secant squared of xy, making the final answer dy dx is equal to negative y secant squared of xy all over x secant squared of xy minus 7. So those are basically the only two types of implicit differentiations I give you. One where when you take the derivative that dy dx is on the outside, or if it's on the inside you have to free it, and then this part is just like what we did up here. You're solving for dy dx. And that's all there is to implicit differentiation.